Welcome! In this Let's Answer video, we're going to be tackling problems in stereoisomerism. In this video, we're going to be tackling questions of the following format. What is the most appropriate way to describe the relationship between the pair of compounds in each set? Are they, and these are the choices, A. Enantiomers, B. Diastereomers, C. Constitutional isomers, D. The same compound, or E. Not isomers? So in the following slides, we'll be looking at a pair of compounds and we'll be determining what is the relationship between the two compounds. And we'll be choosing from the 5 choices we see here. So without further ado, let's begin. What is the relationship between the pair of compounds below? The question is asking us what kind of isomers these two compounds are. And to answer this question, I like to go through a checklist in my head. For these two compounds to be isomers, they need to have the same chemical formula. And it just so happens that these two compounds have the same molecular formula of C3H6O3. So they do in fact have the same chemical formula and are isomers. Now what is the position of these functional groups? Are they the same? You'll notice this carbonyl group on the left is at the end of the carbon chain and is an aldehyde, or is part of an aldehyde functional group, whereas this carbonyl group on the right is in the middle and is part of a ketone functional group. So they do not have the same position of functional groups, nor do they have the same exact kinds of functional groups, and therefore they are constitutional isomers. Specifically, they are a type of constitutional isomer known as a functional isomer, because they have different functional groups. One has an aldehyde and one has a ketone. Now on to the second question. What is the relationship between the pair of compounds below? Let's go through the list again. To check if they have the same chemical formula, I'll be using a shortcut. So all you have to do is determine the number of carbons, the types of functional groups present in the molecule, and the level of unsaturation. If the two compounds have the same number for each of the 3 criteria, then they have the same chemical formula. If you check the compound on the right and the compound on the left, they both have 9 carbons. And they have the exact same kind of functional group. They have a bromo group as well as a double bond. So they have the same number of functional groups. For the level of unsaturation, we're basically saying, do they have the same number of double bonds and triple bonds? In this molecule, they both have 1 double bond, so they have the same level of unsaturation. You might know level of unsaturation as the hydrogen deficiency index, or HDI. And if they have the same HDI, then they have the same level of unsaturation. Next, do they have the same position of functional groups? So if you look at the double bonds, they have a methyl and isopropyl group on one side, and they have a bromo and a propyl group on the other side of the double bond. So they have the same position of functional groups. The double bond is located in the same place on the carbon chain. And this compound definitely has a double bond, a carbon-carbon double bond, so we are likely to see geometric isomerism in the two compounds. Geometric isomerism is where your compound may exhibit cis trans or easy isomerism. If they are geometric isomers, then they are diastereomers. So if you look at the compound on the left, the isopropyl group is located on the same side as the propyl group, whereas the compound on the right has the isopropyl group located on the same side of the bromo group. So they have a different arrangement of groups on either side of the double bond, and therefore they do exhibit geometric isomerism. And geometric isomers are a subset of diastereomers. So therefore they are diastereomers. For this pair of compounds, we have the same first molecule as before, and we have a different second molecule. Now, what is the relationship between these two? So if you go through our checklist, do they have the same chemical formula? You will notice that they have the same groups attached. They have an isopropyl group, a methyl group, a bromo group, and a propyl group. Isopropyl, bromo, methyl, propyl group. And so they have the same chemical formula. Do they have the same position of functional groups? So in this example, the methyl and the isopropyl groups are on one side of the double bond. However, on this molecule on the right, you have the isopropyl group neighbors with the bromo group. So they do not have the same connectivity, and therefore they do not have the same position of functional groups, and therefore they are constitutional isomers. They are not geometric isomers because we are not just merely switching places the methyl and the isopropyl group, but rather we're transferring the methyl group and the bromo group across the double bond. So they do not have the same connectivity. And they are a kind of constitutional isomer known as skeletal isomers. Because they have different carbon skeletons. You'll notice that this methyl group is located at the 2 position, whereas the methyl group over here is located at the 4th position. It is a skeletal isomer and not a positional isomer because we're moving a carbon atom, and therefore we're changing up the carbon skeleton. What is the relationship between the pair of compounds below? So in this example, it's a little more obvious that this compound and this compound have the same chemical formula because they have the same groups attached to the cyclopropyl chain or the cyclopropane chain. You have this ester group, the CO2Me group, and a phenyl group. So they have the same chemical formula and the same position of functional groups. They do not have a C double bond C. So we'll have to check for chirality centers. And there's only one chirality center on this molecule. It is this carbon over here. Now, because we have one chirality center, there's a maximum of 2 to the n stereoisomers for this molecule. So because we have one chirality center, there are only 2 possible stereoisomers for this molecule. So that means that for molecules with only one chirality center, they are either enantiomers or the same compound. Enantiomers will represent the pair of stereoisomers. And if they are not enantiomers, then that must mean they are achiral, and therefore they are the same compound. Now the trick to this question is that they are arranged in a way where if you draw a mirror on the middle of the 2 compounds, then you'll see that the left compound is just a mirror image of the right compound. So this pH group is still on the bottom, and this H is on the top. So they are mirror images. Therefore, they are enantiomers. You can verify this by flipping over this molecule 180 degrees so that we can try to match where the CO2 groups are compared to the left one. So if we draw the compound flipped over, we would have the two CO2Me groups on this side, and the phenyl group will be pointing upwards and the hydrogen will be pointing downwards. As you can see, the pH groups are not on the same side of the molecule, and therefore they are not the same molecule. They are isomers of each other, and therefore they are enantiomers. Next, we have two compounds that are shown in their Fischer projections. So what is the relationship between them? Now both of them have 4 carbons and 4 hydroxyl groups. They also have the same level of unsaturation, so they have the same chemical formula. And they also have the same position of functional groups. They do not have any C double bond C groups, and so we'll take a look at the chirality centers. So each of them has 2. In the Fischer projection, each of these vertices are chirality centers. So the left compound has 2, and the right compound also has 2 chirality centers. Are they mirror images? They are not mirror images, so they cannot be enantiomers. Because only one chirality center, this one, is different in the 2 structures, they are therefore diastereomers. You can double check this by determining the configuration of the 2 carbons. For Fischer projections, when the 4th priority group is on a horizontal, all you have to do is determine the rotation about the 3 groups and reverse them to get the configuration R or S. This hydroxyl group is the 1st priority. This carbon that is attached to oxygen and 2 carbons is the 2nd priority. And this carbon that is attached to 2 hydrogens and a hydroxyl group is the 3rd priority. So the rotation is counterclockwise, which is S, but because hydrogen or the 4th priority is on horizontal, we'll take the reverse of this, and this carbon is an R configuration. And for the 2nd carbon, hydrogen is also once again on horizontal. The 1st priority is this hydroxyl group, the 2nd priority is this carbon, and the 3rd priority is this carbon. So the rotation is counterclockwise. We'll take the reverse of that to get an R configuration. For the one on the right, this chirality center, it looks exactly the same as the one on the left, so this is also an R. And in this one, the oxygen or the hydroxyl group and the hydrogens are exchanged. And you can verify for yourself that this is an S configuration. So this R carbon has been changed to an S carbon, and therefore we have a diastereomer, or a pair of diastereomers. If this were the enantiomer of the RR molecule, then we would have an SS molecule. I also want you to note that this compound is a meso compound. Therefore, it is achiral, an achiral molecule, because this molecule has a mirror plane of symmetry. For example, if we take the mirror image of this molecule, we would have a molecule that has an RS configuration. But because the molecule is symmetric, these 2 compounds are actually the same. So this is a meso compound. Just to visualize it further, So this is the Fischer projection of an RS, or the enantiomer of this mesocompound. But if we turn this molecule 180 degrees around, it will just be the same as this compound over here. So they're not actually enantiomers, they are the same compound. Okay, so to reiterate, the relationship between these two compounds is that they are diastereomers. Next up, what is the relationship between the pair of compounds below? So looking at the structures of the two compounds, they look to have the same chemical formula. They both have 3 carbons, the same carboxyl group, amino group, and thiol group on both of the compounds, or on both of the molecules. So they have the same functional groups and the same level of unsaturation. They only have one double bond, which is this carbonyl group. Now they have the same position of functional groups, and they do not have a C double bond C. So then let's take a look at the chirality center. They both have one chirality center. So at this point, they don't look like mirror images. But let's verify whether they are enantiomers or the same compound by looking at the priority of the groups and determining their configuration. So if they're the same compound, they must have the same configuration. If they are enantiomers, then one must be R and one must be S. So the amino group gets the first priority since it is the higher atomic number than either of the carbons. This carbon receives the second priority because it's attached to sulfur, which is a heavy atom, heavier than the oxygen attached to this carbon. And the hydrogen gets a fourth priority. Because the hydrogen is facing away from you, then the rotation of the groups will give you an R configuration. For the other molecule, we assign the priority group, so amino 1, this carbon 2, this carbon 3, and the hydrogen is 4. The hydrogen is facing towards you, so the rotation that we get here, we'll have to reverse it, and since it is turning clockwise, this is also an R configuration. So both of these amino acids have an R configuration, therefore they are the same compound. Next, we have these two molecules with a cyclohexane chain. So what is the relationship between these two compounds? So they have the same chemical formula and the same position of functional groups. They both have these two amino groups and a methyl group attached on the same carbons. Okay, and both of these are cyclohexanes. They are just represented differently. This one is the regular top-down view of cyclohexane, and this one is the chair depiction of cyclohexane. There are no double bonds, so let's look at the chirality centers. Now, to make this easier, you can either do one of two things. You can draw this as a chair conformation, or you can draw this as the regular depiction of cyclohexane. So let's try doing the second option. Let's draw a cyclohexane. And this amino group is pointed down, so we'll write it as a hash. This amino group is pointing downwards, so we'll also write it as a hash. And this methyl group is written going upwards, so it is a wedge. Take note that as I'm writing the groups around the cyclohexane ring, I'm going in a clockwise direction here. So in the molecule that I'm drawing, I'm also going in a clockwise direction. So what is the relationship between this and this? Well, they are mirror images. So they are enantiomers. if you look at the groups, the NH2 groups are wedge here, whereas here they are hash, and the methyl group is hash, it got turned into a wedge. So because all of the chirality centers have been switched, they are enantiomers. If only one or two of these chirality centers have been switched, then these would be diastereomers. Now let's try this example. What is the relationship between these pair of compounds below? So they look exactly the same, except that their double bonds are in different places. So they have the same chemical formula, same position of functional groups, and they have double bonds. Now, these are actually what are known as resonance structures. If you recall, the benzene ring cannot be accurately represented as one resonance structure, but they need to be represented as two resonance structures, and they are actually an average of the two structures. So we can show the movement of the double bonds using an arrow, using arrows in this way to interconvert this resonance structure into the one on the right. And resonance structures are representations of the same molecule. So they are the same molecule. This is true for any pair of resonance structures. They are just representations of the same molecule. And you can also see that the double bonds aren't actually changing in their configuration in space. They're always in the cis configuration. So there's no geometric isomerism that is occurring in this molecule. Next, what is the relationship between these pair of compounds? So again, let's go through the checklist. So are they in fact isomers? Or do they have the same chemical formula? So you might panic when you see so many functional groups on a molecule and they have more than one stereocenters. But if you focus your attention on the hydroxyl groups here, the second molecule has the hydroxyl groups transformed as carbonyl groups. So in fact, these are not actually the same molecule. They do not have the same chemical formulas because they do not have the same functional groups. So they do not have the same chemical formula, and therefore they are not isomers. And they are different compounds. Okay, and that was our last problem. Subscribe to this channel for more chemistry problems, and I'll catch you in the next video.